everyone. Welcome back to another episode of Geoscience Explorer. Our planet is a dynamic place. It constantly recycles its crust and creates new rocks from any component it can use. Rocks are made of minerals stuck together or pieces of once existing mineral matter. Geologists have come to define rocks into three main types: sedimentary, igneous, and metamorphic. These rocks are connected through the rock cycle, a continuous process where rocks form, change, break down, and reform over time. A rock can take any path in this cycle depending on the environment it encounters. Today, our focus is on sedimentary rocks, the storytellers of Earth's history. Sedimentary rocks record ancient environments, climates, and even life. Earth has not always been the way it is today. A desert in the present could have been a massive lake millions of years ago. We know this because sedimentary rocks hold clues based on the minerals present and how they are arranged. They also hold fossils, which are remnants of once living things, giving us a window into life of the past. Beyond that, sedimentary rocks provide water, fuel, and raw materials, and form aquifers, contain coal, oil, and natural gas, and even help build our homes and cities. In short, sedimentary rocks don't just tell a story, they are vital to life on Earth. So, what does a sedimentary rock's journey look like? First, weathering begins to break down an existing rock into loose sediment. This weathering might be physical, chemical, or even a combination of both, slowly weakening the rock's surface piece by piece. Eventually, the sediment becomes close to a riverbank where erosion steps in. One day, a strong storm sweeps through, and the fast moving current grabs the sediment and carries it downstream before tossing it onto a distant shore. Over time, the sediment finally settles, resting long enough for deposition to take place. Layer after layer begins to build as more sediment buries it from above. With enough time and pressure, compaction squeezes these layers tightly together, and what once was a simple grain of sediment transforms into a new sedimentary rock. Sedimentary rocks form from sediment, which are loose pieces of rock, minerals, or biological material. To become a rock, sediment must go through processes that bind it together. The first is compaction. This occurs when layers of sediment are buried, and the pressure from above squeezes the grains tightly together. Then there's cementation, which is when minerals dissolved in water act like glue, binding the grains into solid rock. These processes take thousands to millions of years, slowly transforming loose sediment into rock. But before sediments become rock, they often start as part of existing rocks that are broken down through weathering. There are two categories of weathering: physical weathering, forces like ice, wind, or waves that break rocks into smaller pieces without changing their chemical makeup. Then there's chemical weathering, which alters the minerals in rocks, either by changing the minerals or new ones crystallize. An example is oxidation, which causes rusting. Imagine a car. A car's frame is made of metal, which is composed of iron, and because oxygen and water are present, iron will react to them and alter iron into iron oxide, known as rust. This happens to rocks because water and oxygen can alter minerals when exposed. Once sediment is produced, it can move through erosion, the process where water, wind, ice, or gravity carry sediment to a new location. When sediment finally settles, it is called deposition. Over time, deposited sediment form layers called strata, which are like pages in a book recording Earth's past. A perfect example is the Grand Canyon, where thousands of feet of strata reveal millions of years of geological history. All rocks tell a story of the environment they originated in. Geologists can read their story by looking at key characteristics that are present. It is important to understand these characteristics in order to properly describe them and easily identify between sedimentary, igneous, and metamorphic rocks. Here are some important ones. First is composition. This is simply what the rock is made of, such as the minerals present. Next is texture, which is how the minerals are arranged and relate to each other. Texture is very useful in distinguishing among rock types, but we will focus on how it relates to sedimentary rocks in this video. Some examples include grain size, sorting, and grain shape. Color is probably the first characteristic to recognize. and actually only somewhat useful. One such case of using color is that a reddish-brown color typically indicates that iron is present in a rock. Density, which is how heavy something is based on its size, is not the same thing as weight. To illustrate this, if you pick up a small rock and it is heavier than expected, the rock would have high density. Hardness, or how easy it is to scratch a rock. This comes from the Mohs scale, which calculates the hardness of minerals by going from 1 to 10, where a human fingernail is 2.5 and a diamond is 10. And finally, we have structure. A rock's structure is a feature that can indicate how the minerals are arranged, layered, fractured, or deformed. Let's show each of these characteristics by looking at this piece of sandstone. Sandstone's composition is mainly the mineral quartz. It's hard to see closely, but this one has round quartz grains, with the pieces being the same size. We can describe this sandstone's texture using a chart showing sorting, angularity, and sphericity. We would describe the sandstone as very well sorted, and the grains or pieces of the quartz are well rounded with high sphericity. Sorting describes the range of grains and illustrates the comparison of all the different sizes. Sphericity means how closely the particles look like a 3D sphere, while angularity means the grains have sharp edges. The color in this sample is yellow. Now, density is hard to determine without picking up an actual specimen, but we can infer that this sandstone is moderate in density because quartz itself has moderate density. Sandstone has high hardness because of quartz. This specimen does not have much structure, but structure is more prevalent in igneous and metamorphic rocks. Now, geologists make these observations because they are able to describe the environment they were based in with the characteristics like sorting, angularity, and sphericity. So, our sandstone form in an environment that experienced intense erosion across a long distance, such as a beach. Transportation over a long distance also can increase weathering in mineral grains. These characteristics are helpful in understanding the first type of sedimentary rock, clastic. Clastic sedimentary rocks form from broken fragments of other rocks, called clasts. Clastic rocks reveal the energy and environment they formed in, and here are some examples. Conglomerate. This formed from rounded pebbles of various sizes and indicate an origin from fast-moving water, like a river. Because the grains are large, it would be described as coarse grains, and this is an example of poorly sorted. Another example is shale, formed from fine clay particles and suggests calm water, like a lake bed. The clay particles are too small to see with our eyes, but the particles are platy, plate-like, or flat, so shale has low sphericity. Clastic rocks are essentially nature's recycled rocks, which is why they are also called detrital sedimentary rocks. Either way, the broken fragments will be packed together through compaction and cementation to create the rock. Chemical sedimentary rocks are created when minerals precipitate out of water, meaning dissolved mineral ions crystallize and settle as solids. An example is limestone, the most abundant chemical sedimentary rock. It forms when calcium carbonate, made of calcium, carbon, and oxygen, precipitates out of water, often in oceans. Some limestones form from fresh water, so long as calcium carbonate is available. Some don't even need bodies of water, like travertine, found in caves and hot springs, and speleothem from water dripping that leaves mineral deposits behind. Chemical sedimentary rocks record the chemical conditions of the water they formed in, making them important clues, such as changes in sea level. And the last type is organic sedimentary rocks, and these rocks contain remains of once living organisms. A perfect example is coal, which forms from plant material buried in oxygen-poor swamps. Normally, dead plant material would be broken down by decomposers in an environment, but if oxygen is removed, plant material will settle to the bottom. Over millions of years, burial, compaction, and chemical changes transformed the plant material into carbon-rich coal. Other examples include biochemical limestone, made from accumulated shells or skeletons of marine organisms. Organic sedimentary rocks literally preserve life, giving scientists clues about ancient living things and their ecosystems. Sedimentary rocks are Earth's storytellers. We can use characteristics to better describe the rocks in order to understand their origin. By recording all the intricacies, we hope to understand about Earth's past and prepare for the future. From sandstone cliffs to coal deposits, these rocks are essential to our planet, supporting ecosystems, human life, and industry. Thanks for watching. Stay tuned for more rock solid facts and stellar vibes.